Right. Hi, everyone. Thank you for joining. Thank you for having us here. My name is Dimitrios. I'm from Greece. And with me?
This is the presentation. And I'm José Leitão, and I'm accompanying him with the talk.
So here are a few things about me. So I'm engaged in computer security since 2002. I was member of one of the first reverse engineering groups back in Greece. I started my career as a network security engineer for about 10 years. Then I moved into developing for almost 5 years. And the last 6 years I focused mainly on mobile security, while before I joined Microsoft's threat intelligence team as a senior security researcher, I was leading another team, actually it was his manager, so which was conducting malware abuse for the Google Play Store. Besides that, I'm a father of two, a boy and a girl, and in my free time I try at least to write and play music.
All right, now it's my turn. My name is José Leitão. I like to wear rubber duckies at weddings. I'm engaged on security since 2019. Dimitrios is my previous boss. And then we managed a team together. Currently, I'm leading a 100+ Android reverse engineers team at Cognizant here in Europe and a few more in offshore. Also, like Dimitrios, I'm a father of one, but it's a 4-legged creature. And on my free time, I'm a surfer and a rock climber.
All right, so let's jump right into the outline of this briefing. So first of all, we're going to talk about the core principle of understanding is defending, and here we're going to see how important it is getting to know how the malware works, since this can help us to defend against it. And then we're going to take a look at the modern Android malware landscape. We're going to see what's new in the Android ecosystem when it comes to malware. After that, we're going to see some dynamic analysis evasion techniques. We're going to see how malware tries to identify if it's being watched. And we're going to go through the most creative ones, not necessarily the most technical ones, the most creative ones, as you're going to see. After that, we're going to do about the same about static analysis evasion techniques. We're going to go through a specific showcase, which is very interesting, at least for us. And we're going to wrap up with conclusions and takeaways. All right, so I won't lie to you, writing malware is a form of art, right? A form of dark art, but it takes quite a lot of skills for someone to be good at this. And I'm not talking, of course, about clicking a couple of buttons in malware generation utility in order to do such a thing. What I mean is writing something which is unique, something which is clever, sneaky for us to detect. And now on the other side, us, the malware researchers, security researchers, we have to be one step ahead from the malware developers. So in many cases, we have to think as they do, but most importantly is that we have to understand what they do and how they do it. So the key word here is understanding. And when it comes to understanding, it's an ongoing process where we continuously have to go through have to dive into the malware mechanics and see how it works, how it does what it does. We have to recognize potential evasion techniques in order to improve our detection systems. We have to learn about exploitation tactics because in many cases adversaries are using them in order to compromise system and user data. And do what we are doing here. I mean, engage with the cybersecurity community in order to exchange info about threats and defense strategies. And now José is going to walk you through the modern, a picture of the modern Android malware landscape.
Yeah, so let's talk about how the modern malware looks like currently. There's two main categories. First one, malware in the market. Market is applications where you can get them on Play Store or Amazon Store or other official marketplaces created by manufacturers, Samsung, Xiaomi, etc. These Android malware tend to hide the malicious behavior in a bit advanced ways, more advanced ways than the off-market. Now, the off-market, these are applications that you can get, well, anywhere else. On a website, a link in an SMS, a friend send you, be careful with those, I have plenty of them, or even through ADB, directly through ADB. In our opinion, off-market malware tends to be easier to detect. Why? They don't have to survive the marketplace's evaluation process. And if they get caught, they don't really have much to lose. So why burn hiding techniques, right? They typically use packers, obfuscators, protectors to make the reverse engineering part a bit more difficult. But they don't have to rely on this that much, or they'll raise red flags. And those red flags for us are honey. We smell it a mile away, so they don't want that. Basically, on the operation side, what they do is abuse services. Accessibility services, notification listener, even root access to spy on you or to collect financial information and data that they can use. Now, let's see how the market malware looks like. What's the phases that it goes from start to end? First one is motivation, commonly profit. And that's why the most prevalent malware in the Play Store is some sort of billing fraud. SMS fraud, toll fraud, call fraud, anything that can subscribe you to a service that you don't want or don't even know of. Next one is the development phase. Now, this is not a one-off, just drop the malware and go away. No, this is a continuous process. They have teams, huge teams of engineers fighting for the user's money. The stealthier ones and the most innovative ones win. Now, the publishing phase, and this is a cool one. They have certain tricks amongst themselves. One of them is, for example, they publish an unweaponized version to bypass the marketplace's evaluation processes and to collect users. 1,000 users, million users, depends on their target. Once they reach their goal, they update a new version and infect all the collected users. So this is one of the most used tactics. Last year, Google introduced a new defense mechanism against this. They need new developers to have at least 20 testers for 14 consecutive days before they can publish an app. Cool, right? So malware developers adapted. They started buying old accounts. And believe me, they have money. Let me say this again. Believe me, they have money. Whoop. Sorry. Okay, and finally, the unpublished phase, which culminates on the app being detected and banished. Don't worry, they'll be back again real soon.
All right, now for the sake of completeness, let's go through some basic malware categories. And when it comes to classification, and the virus vendors are classifying them differently, but we're going to do our best in order to get some common points. So we have, of course, backdoors. When it comes to mobile, a backdoor may allow an adversary to remotely connect to your device and start running unwanted code. We have downloaders. Again, when it comes to mobile, there are apps which have their main purpose to download and install other kind of malware. Usually they are something like a service. They are offered like a service which other malware developers can use in order to distribute their own malware. We have ransomware, a type of malware which takes partial or full control of the device and demands some ransom in order to release this control. Now the difference between the mobile ransomware and the PC ransomware is that mobile ransomware doesn't have to encrypt the device's data. So what they do usually is using some kind of a privileged API like the administrator API, so they log your device, or they might use some kind of an overlay in order to cover the screen, so the user will lose access to the device and has to pay the ransom in order to get back the specific access. When it comes to phishing, I guess it's pretty much trivial. So what they pretend to be some kind of a trustworthy source, while they are after your credentials, your financial data, private info, and so on. And then we have Trojans, which is a type of malware which pretends to be innocent while it has some kind of a malicious module. Now, Google Play.
And then finally, we have the Google Play categories. They're not the same as the other ones. They have their own. And these are the most known or most prevalent. First, billing fraud, SMS fraud, call fraud, toll fraud. Get my money. Then spyware and commercial spyware. They tend to get your contacts, your SMS information, your calendar information, or spy on your actions. Then you have spam, which is, well, you all know spam. You'll either spam you or your friends. And finally, maskware, which is kind of a new category. this category is something like the application says it's something, a game, but then depending on the country you're in or who you are, it will show something completely different, like a casino.
Right. So, all right. Now, let's assume that you are some kind of malware developer. You managed to, as José before said, publish your app to the Play Store. You managed to get some thousands of users. So now it's time to weaponize your app in order to start making some profit. And here is where the actual struggle comes due to the fact that apps usually go through ongoing dynamic and static analysis because especially in large marketplaces, these apps are going through this process repeatedly. So we're going to move now to the main part of this briefing, which is dynamic analysis. As I said before, we're going to see the most clever ones, the most creative ones that we choose, according to us, of course. And once again, they don't have to be very technical. So I hope everyone will get them. So when it comes to dynamic analysis, the main objective is to understand, the malware developers to understand if their malware is being watched, and if it's being watched, somehow don't expose the malicious behavior. So that's the main point. And the first one is one of the simplest tricks, and has to do with excluding some certain libraries. So what I mean by that, you probably know that mobile devices come with different CPUs supporting different instruction sets. So being an Android developer who works with native code means that you have to compile your APK in a way that supports all these libraries, all these architectures. Now, here's a simple trick. Due to the fact that antivirus vendors are mostly using, I mean, it's common to use x86 VMs in order to perform the tests. So what they do, they simply exclude the specific libraries. And if you try to run such an APK to an x86 VMs, for example, you're going to get the following error, especially in older Android versions. While even in newer Android versions, you're going to get crashes, or you're going to get some error or something. So your whole pipeline collapses with just a simple trick, just excluding some certain libraries, and the whole thing just collapses.
And the next one comes, or should come at no surprise for anyone here, which is detecting the testing devices, right? They collect some of these things here on the screen and evaluate them either locally or send it to a command and control server. So let's see what they most want to collect. The model, self-explanatory. The fingerprint, where they check if the device is signed with debug keys. Then manufacturer and brand. So let's say you're a malware developer. You want to publish in the Play Store. You assume that because it's Google, they're going to test it with Pixel devices. So just remove it from your target and we're good to go. Oh, that's also me. Yeah. And then the SIM operator, so the card you get from your provider. You can use these API calls here to understand more where the user is from based on that particular codes. And then you can either target or avoid specific countries. Sometimes you want to avoid, I don't know, China, or sometimes you want to target, like this example here, South Africa. And this is exactly what you're doing. They're launching a campaign on a South Africa SIM operator.
All right, and this one is one of my favorites, I guess from the point of creativity. So what you see in the specific screen are devices. Which devices are connected to a cable? So how someone can use this kind of info in order to, let's say, evade dynamic analysis or something like that. So the fact that these devices are connected to a cable maintains their power level, their battery level is always full, right? So if you think about it, your devices, the device that you have in your pockets, can be always full. So, as I said, this is exploited by malware developers in a clever way, from the point that Android operating system, from time to time, sends an intent, a broadcast, actually, which, in order to inform the apps which are installed in the device, to inform them about the battery levels, if the device is plugged. It has actually a lot of useful info there. So what they do in the specific case is just register a broadcast receiver, which listens for this kind of broadcast, this kind of intents. So they get the intent, they check if the device is plugged, they check if they can check the battery level, combine it with other type of info in order to be more, let's say, precise, and do all that before they expose, as I said before, some kind of a malicious behavior.
And then another creative one. Are we published? So again, malware developers know there's a process, an evaluation process every time you publish an application to the Play Store. It's not immediately accepted. So what they do is they try to check if their own app is already published or not. So for example here, this method here triggers the malicious behavior. But first, they need to go through a check. And that check is sending a request with their own package name to the Play Store saying, are we published? If not, then why display the malicious behavior? Why take the risk of getting banned even before they published? So let's just stay idle. If not, then trigger the malware. And here we've talked about Dimitrios' favorite battery. Let's talk about my favorite. Mobile measurement partners or referrals. These are legitimate ways to find out where you install the application from. If you install the application through Google Play's feature of invite a friend or clicked a particular marketing campaign ad, that's a non-organic event. If you discovered the application by yourself, clicking on your own on the Play Store or installed through ADB, that's an organic event. So by now, you already know where I'm going with, right? If you click an ad, which is non-organic event, you're already inside their trap. So just launch the malware behavior. If it's a non-organic event, let's just stay idle, keep it on the shadows, and don't waste the time. We have an example of this. So, first one, registered referral listener. In this case, it's an app's flyer conversion listener which listens to marketing ad campaigns. Then we listen to the action, a callback with multiple things of information, who you are, what's the country, is it non-organic or organic, and finally, the real code. If it's a non-organic event, let's go to the malicious behavior. If it's an organic event, stop. Just go to a decoy application, decoy activity, just do your normal job, and that's it.
So, yeah, next one. All right, and dynamic content. And when it comes to dynamic content, the first thing that comes to my mind is web views. And why web views? Because they are really powerful. So you can imagine that even development frameworks like React Native or Ionic are literally based on web views. Someone can build a whole app with just this single component. So a web view has another powerful, let's say, feature which is called JavaScript interface, which can allow the web content which is loaded to this component to trigger, to invoke Java methods. So that's once again, very powerful. And once again, it's exploited by malware developers in a clever way. So what they do is usually combine it with some kind of device fingerprint or something. So gather everything, send it to a command and control server, and depending on this data, the command and control server will send something else to be loaded to the specific web view. So if, let's say, the decision is that the device is the testing device, the web content that is going to be sent is going to be something innocent, or if it is an actual device, a user device, then it's going to send something which is supposed to be malicious and perform some kind of malicious behavior. Now, the last one which we choose, although it's not some kind of dynamic analysis evasion techniques, it's something more, I would say, social engineering, and is used by off-market apps. So what they try to do in this case is try to convince the users for their origin, for their legitimacy. So what you see here is just pretending that they originate from Play Store, for example, for a trustful marketplace, while everything that you see in the specific screen is simple screenshots, the reviews are fake, everything is fake. So be aware of these kind of tricks, because despite the fact that it seems to originate, like I said, from Play Store, it's not. And I can spend the rest of this briefing talking about this kind of stuff, about dynamic analysis evasion techniques and what they are doing in order to bypass our defenses. To add to what we said so far, we have root detection. Of course, they are going to check if the device is rooted, because usually testing devices are rooted. Debugging detection, if their app is debugged, or some kind of a hooking hook detection, like some kind of a binary instrumentation framework, like Frida or something. Or even network. And what they do when it comes to network, they implement their own SSL pinning or add some kind of custom encryption layer, so they hide the communication between the client and the server. But the most clever ones, the ones that it's also hard for us to overcome, are the ones that have to do with user interaction. So we saw them checking the device, if it has some files or if it has some photographs or something. Or they might expose the malicious behavior after going through some kind of a complex user interaction, right? They might ask the user to create an account or something, which is something which is hard for us to overcome from the point that all these things that you saw before, I mean, the dynamic analysis part belongs to usually to some kind of a pipeline. So it should be automated, simply said. So it is hard to interact with the malware in a clever way and be able to bypass all this kind of stuff. All right, so let's now move to the second part, which is static analysis. And when it comes to static analysis, malware developers have to bypass a couple of defenses, including signature-based detection. Simply said, you give a file. This file is checked for known byte patterns that have been previously identified in malware. We have heuristic analysis. We give some characteristics, including some suspicious API calls, or if the app is packed, or if it's obfuscated somehow. And we can come up with some kind of a decision regarding if it's malware or no. We have machine learning and artificial intelligence, where, once again, AI models are trained in order to identify malware based on some specific characteristics. And if everything, let's say, fails, if there's no decision made so far, then a reverse engineer, a malware analyst can take the call and combine these two, let's say, type of analysis in order to come up with a decision. All right, so the first one, when it comes to static analysis, is about entry points. And when we talk about entry points in malicious code, I'm referring to the line where the malicious code will start to get executed. So for those who are not familiar with Android, so Android apps usually have one main entry point, which is the main activity. We can identify this main entry point from an entry in the Android manifest. Once again, every Android app has a manifest where it declares components, activities, and all this kind of stuff. And this is very characteristic for the main activity. So it was some kind of, let's say, common practice from us to search for malicious entry points within the life cycle of this main activity. Although since then we've seen many few new entry points, including services. They start the malicious code from some kind of broadcast receiver or a content provider, and more often from the application subclass, despite the fact that it is not that common, I would say, for developers to extend the application's subclass due to the fact that Android uses the default base one. Now, in one case, we spotted the following when it comes once again to the application subclass. So we saw this call here, which loads a native library. That's what it does, nothing more. So it loads a native library, although if you check the specific application for native calls from the Java side, you won't be able to find any. And actually, you don't need it due to the fact that when a library is loaded using this way, I mean using a specific API, then it will call the JNI onload. The JNI onload will run everything that is within the specific method, and you have your entry point. Now the next one is very interesting from the point I'm going to explain. So it was discovered from researchers at McAfee, and what was happening was the following. So imagine that you are a malware researcher, and you want to identify what is wrong with a specific entry, what is wrong with the specific, let's say, provider. So what you are going to do, of course, is decompile the provider and try to see what's wrong there. If you do such a thing, you won't be able to find something because everything was empty, return null, or something. I mean, everything was empty. Nothing interesting there. So where's the catch? So the catch in this case is the specific entry. And up to this point, this entry was ignored. I mean, at least I don't know someone that would pay attention to this specific metadata entry. So what this entry will do is trigger a Java call, from the Android framework, which will do the following. It will perform a query to the specific content provider. Content providers, though, are dynamic components. They have to be created somehow. They're not somewhere, they don't stay somewhere, so they have to be created. So in order to do such a thing, the operating system will trigger the application subclass, and the application subclass will do everything in order to create the content provider. Now, so let's go through the full chain. So what happened is we have a metadata entry, which, as I said, was usually ignored. And through this metadata entry, you are able to run your native code. And this is exactly what happens here. I guess many of you have installed already some kind of Android app in your Android device, so you don't have just to install an app, you have to click on it in order to run, right? So in the specific case, the only thing that you need is just to install the app, and the app will auto-start by itself, right? Yeah, that's it. I mean, it's not something, but it is impressive from the point that the only thing that you have to do is just to install the app, not click on it, nothing, no other user interaction, that's it. Okay.
Let's now talk about reflection. We had the speaker yesterday talking about reflection. He made it seem like it was really hard, and he was 100% on point. It's still one of my favorites. It enables so many crazy ideas, legitimately in a gray zone or even malware. So reflection is on this package here and allows you to get access to the class of any object, to dynamically create instances of classes and access fields and methods, and get classes, interfaces, fields, methods at runtime. So let me explain this in a way that everyone can understand with this example here. This is how typically you get reflection. For example, this here is the class for name. Basically, you just pick a string, text, character, any text format, you send it to this method, and it will run a class, a method, an instance that's been developed by you, or it's in the Android system. So that allows magic to happen. You don't have to have the code pre-done before shipping the app. You can do it dynamically. You can encrypt the string to make our life, the reverse engineers, even harder. Let's go for an example for you to perfectly understand this. This code here, not using reflection, it's a simple 5-line code, has a string, you get the character at a certain position, you get a string builder, and you append it to it, right? This is a reverse engineer's dream. I would be out of a job if everything was like this. Then let's see the same exact thing with reflection as a pain in the ass. There we go. Now we're going for a coffee. We'll let you see this and we'll come back real soon. So basically this is what we see. But I've been a good boy and not even encrypt the strings. And if you've noticed, this isn't even Java. This is on the native side. This is C. So you can use it on Java, you can use it on C, and it's really hard to read, even in plain text.
All right, so I guess this one doesn't need much of an introduction when it comes to cryptography. I guess cryptography has been abused by malware developers and malware families for a lot of years, I would say. So cryptography apparently has been abused due to the fact that you can't use it in order to hide things, right? So we saw them hiding strings, using some kind of a custom encoding in combination with a simple XORing operation or something in order to hide strings, or even to hide payloads, or as I said before, to protect the communication between the server and the client and so on. So malware developers are not always that clever. So take a look at this specific code snippet. So what the guy, I guess the guy, did in the specific case, So he used AES encryption in order to encrypt the strings, encrypt API calls, everything through reflection, everything through encryption and something. So you were, in simple words, you weren't able to find a suitable, let's say, string in order to create some kind of a signature to catch at least a specific sample, right? Although, if you search a little bit more, you will find the key and the IV there, which is, as you said, very unique, so you can simply create signatures based on this. Right, so the next one is steganography, and once again, steganography, I guess it could be absent from the adversarial toolbox. So especially when it comes to Android, the Android packaging is very convenient to do such a thing. It's simply a zip file, and you can hide whatever you want inside it. It's just signed with, by the developer to protect the integrity, nothing more. So here's an interesting case. We indeed decompiled the specific file, and we found this image here. So now if you open the specific image, you won't be able to see something malicious or something even scary or something. Until a specific date comes, it was something like 2019. It's an old sample, but once again, it's very interesting. It's one of the hardest to at least analyze. So at that point, this malware will load the library, which library will do whatever it takes in order to extract a payload from the image that you saw before. Now, this payload is a downloader. It will just communicate with the command and control server, download the banking Trojan, which will actually hunt for your credentials.
And the next section is dynamic code loading, which is basically why Joker, the very known malicious code, is the most prevalent malware in various markets. So what does dynamic code loading do? It enables you to download or extract a payload and then run it in the application's memory. We could do it like for the steganography that Dimitrios showed you. We can do it for files such as text files, Java bytecode, Dalvik bytecode, native files, and even JavaScript. So it allows you to pick codes that it's not shipped within your app and run it. That's basically it. Now, obfuscation and packing. And this is not only used for malware. It can be legitimately used to protect intellectual code, right? Intellectual property and code. This serves the sole purpose of hiding code from static analysis tools, automated static analysis tools, or reverse engineers. It can scramble the classes names, it can insert garbage code into the application, or like this sample here, it can include difficult math operations to further confuse you. Remember that they want to confuse you. As long as you're confused, you're looking for something else rather than the actual malware. And on the packing, we have an example here. When they pack an application, if you decompile the APK, you won't see much. You will see, maybe if you're lucky, empty classes, or most likely nothing at all. You'll see a file. What happens is, there you go. Everything starts from the entry point, the application class that we've talked about. Once the application class jumps in, the code will be loaded into the application's memory using dynamic code loading. And the only way to get, the two only ways to get the code is by either manually unpacking it, which I don't recommend to anyone, or dumping the application's memory using Frida or other tool of your choice. And now we're going to jump to the showcase. Yeah. Oh, there we go.
All right, so yeah. And now we're going to go through a showcase to see everything in action. Try to follow me at least. So this app has about 3 stages, and it's a very interesting sample. I think I presented it once again, although I was focusing on a totally different aspect. So it's simply said a toll fraud app, which tries to once again charge the user without the user consent, of course. So this, the malicious flow, let's say, starts in the application subclass that we said already. And what actually is happening here is that the app will start another thread besides the main thread. So what this thread will do is just perform an HTTP request to the Play Store to verify that the app is published or no. The trick that we already talked about. If it is published, then we'll start the following. So we'll call this method J, and this method J, what we'll do, just go through the application's assets and try to find the file which ends with 355. So it's this asset here. After that, it will create another file, a temporary file, to the cache directory. And from there, it will just copy the asset file to the cache directory, nothing more. Next step is to create, actually, a XOR key out of strings which are, let's say, spread here and there. So we'll create a XOR key. And finally, create another file, a temporary file, which is empty, and send everything to this method J here. So it will send the application context, the encrypted file, the key that we said about, and the empty temporary file. This method J will do the following. Once again, first of all, it will calculate the SHA-1 digest of the key that we saw before, and out of this digest, it will create an AES key. It will use this AES key to decrypt the file that you saw before. And using this file, actually this file is a native library, so it will load it using the system load method. And finally, it will trigger a native method, which is this one here, passing the XOR key. Right? So let's summarize what we have as the first stage. First stage, first of all, create the key, the way that we saw before, and then get the file from the assets directory in order to decrypt it and create another file, a native file, which is loaded now in the application memory. So that was the first stage. Second stage, something similar, a little bit different. Go once again through the assets of the app and try now to find another file which ends with 300. This is the second payload. We will get this payload. It will XOR it with the key that we saw before. And what will happen here is the second stage, which is an APK. So it will XOR the file once again. It will create an APK, and this APK will be loaded using Dex class loader or something. So now this APK will communicate with a command and control server in order to download another payload. So this payload will be saved in the cache directory, and then this star SDK method will use, once again, dynamic code loading in order to load a specific class and call a specific method, which method will communicate once again with a command and control server in order to now load another payload. So we have already 3 stages, 2 payloads from the assets directory, another 2 payloads that they were downloaded from a command and control server. And here's the summary.
Yeah, this is the summary. So basically, you're very lucky to see this application. This is a hand-picked one. You don't normally get everything that you see here. You don't get the DCL together with the Are We Published together with the steganography. It's hard to get. So summarizing everything that you've seen here. Application entry point where everything starts. Then the execution guardrails, Are We Published, DCLs, 2 payloads and 3 stages. Steganography, cryptography, dynamic code loading, obfuscation, still the same app, native code, and this is all we can get in one app, which is normally spread among apps. So Dimitrios is going to do the wrap-up now.
Yeah, actually even the newest apps that I have been reviewing recently, they use about the same flow, so it seems to be very successful, so just pay attention. All right, so let's wrap up everything. So I can't stress out more how important it is, what is the actual danger here when it comes to mobile apps and mobile devices. It's an ongoing struggle that we have to be one step ahead from the malware developers always. And it's although everyone should be on board, including researchers from other fields, and most importantly, users who must inform themselves about this kind of threats. So thank you very much for your attention. If you have any questions, we'll be happy to answer.
Thank you so much.